Thank you, and good morning, everyone. And thank you for joining us for our discussion on isolation and drying of peptides and oligonucleotides. So as we all know, and we've talked a lot already yesterday on how the demand for oligonucleotides and peptides has rapidly increased over the last few years. And I think everybody in this room is pretty excited about that and hopes that that continues in the future, and I think we expect that to only continue to grow. While this demand is really good, it also shines a bigger light on some of the production bottlenecks in the typical methods used to produce oligonucleotides and peptides. So for the next few minutes, we're going to talk about one such bottleneck, and we're going to concentrate on the drying of these molecules. So before we jump into that, I'll very quickly introduce who Fluid Air is. So as was mentioned, Fluid Air is a division of Spraying Systems Company, the world leader in spray nozzle technology. So Spraying Systems has been around for over 80 years, and Fluid Air has been around for over 40 years, providing the pharmaceutical industry with powder processing technology such as fluid beds, high shear granulators, size reduction mills, and now our polar dry electrostatic drying technology. So we're headquartered just outside of Chicago in the US, where we have our main manufacturing facility and our largest pilot laboratory facility. We also have manufacturing capabilities in Shanghai, as well as trial capabilities in Shanghai, in France, and in Australia, where we can stay close to our global customers. So now I'll jump into what electrostatic drying is and how it can fill a needed role in the production of oligonucleotides and peptides. So we all know when we think about drying materials such as these, lyophilization is the first thing that comes to mind. This is the industry standard. It's been the gold standard for decades. This is just how you dry temperature-sensitive molecules. It works great, it does its job, but it also has quite a few bottlenecks that we're aware of too, mainly in the long batch cycle times and the high energy cost of those cycle times. So an alternative could be spray drying. However, we also know in spray drying, you typically need to achieve rather high temperatures that could damage these molecules or cause impurities. So that's where our polar dry electrostatic drying technology comes in. So we're able to, through our technology, get the continuous or rapid batch process of a spray dryer without the need to reach the extreme temperature conditions, which allows us to dry temperature-sensitive molecules such as bacteria, enzymes, antibodies, peptides, and oligos. So when you take a look at one of these dryers, it looks very similar to a normal spray dryer. So at the top of the dryer, you have the liquid feedstock being atomized into droplets by use of a two-fluid atomizer. But here's where things start to change. So as those droplets are formed, we impart a light electrostatic charge to those droplets. And that allows us to dry more efficiently at lower ambient temperatures. But we'll get into how that works a little bit more in a few minutes. So as those droplets travel through the chamber, they're exposed to a cyclonic flow of warm nitrogen gas. This is where the wet droplets are going to start to become dry particle. In our production scale models, that chamber is lined with a flexible, removable liner, which allows us to keep the particles from adhering to the chamber wall. And this allows us to keep our yield very high for these very expensive molecules. Traveling down to the bottom of the dryer, now we have those particles separated from the gas stream by use of high retention filters that can capture particles down to 0.3 micron. We back pulse those filters to expel any material that becomes embedded in the filter such that they don't stay in the process and can rapidly move down into the collection vessel. The resulting drying gas is then passed through a HEPA filter, dehumidified, and then reheated and recycled back through the process. So this allows us to utilize nitrogen to remove oxygen from the operation completely, but it also allows us to more efficiently use the nitrogen by recycling it through the process instead of having a single pass through. So back to how does the electrostatic charge actually allow us to dry more efficiently at lower temperatures? So here I have 4 phenomena that I'll discuss in no real particular order, as each one of these, the magnitude really changes depending on the process conditions and the composition of the liquid feedstock. One of the first ones is probably the easiest to understand, is that as we have like charged droplets, they will start to repel each other in the dryer and allow the drying gas to more effectively reach the areas of the spray, especially near the center of the cone, where traditionally it would be very difficult to get the gas in that region. We also have Coulombic forces inducing greater heat transfer within the dryer. We have electrostatic induction within the droplet. Again, this is very formula specific on whether or not this is really a factor or not. And then also increased water vapor drift caused by the electrostatic field in the dryer. So what that gives us then is the combination that allows us to now get the results we're looking for, which is dry particle with a much gentler drying cycle. So it allows us to get that powder on demand quickly through the machine without the need to reach excessive temperatures to be able to finish the drying cycle. So again, here, what we believe we have is really the best of both worlds, is we can take the quality of material and the high yield of a lyophilization process with the speed of a spray dryer without the high temperature degradation of the materials that we're drying. So I'll go through a few case studies here to help illustrate how this technology can fit in the oligo and peptide space. So this first study was done in conjunction with the LyoHub consortium that is based out of Purdue University in Indiana. So during this study, we used 2 different formulations. One was using BSA as a surrogate at 10% solids in an aqueous solution. The second was using that same BSA, but only at 5%, and using 5% trehalose as a stabilizer. The lyophilization was conducted at LyoHub's facility in Purdue University, where we dried 200 milliliters of solution in a 70-hour cycle. We also took those same materials in our pilot laboratory in Naperville on our Polar Dry Model 001 R&D scale dryer. Here we dried 1,000 milliliters, or 5 times the amount of liquid feedstock, in just under 4 hours. So you can see the extreme time difference to be able to generate the materials. But as we all know, being able to generate powder fast doesn't do us any good if the quality of that suffers. So we want to measure those materials to see how our drying process affected the material versus the traditional lyophilization. So here first we look at the solid state NMR that was collected on all of the samples, and we see the relaxation times between the electrostatically dried materials and the lyophilized materials are not significantly different. So this makes us happy. Then we look at long-term shelf stability of the collected materials. So here we looked at 3 different ambient storage conditions at 4 degrees C, 20 degrees C, and 50 degrees C. As you can see from these tables, at 4 degrees and 20 degrees, we see no significant degradation across any of the samples. When we get to 50 degrees C, we see with the 5% trehalose as a stabilizer, we also see no degradation in the samples. But without the trehalose, we do start to see at 50 degrees C a little bit of degradation over the 12-week period. But we also see that curve is a little sharper with the lyophilized powder than it is through the electrostatically generated powders. So then we take a look at the product itself coming out of the dryer. So on the right-hand side, you see the nice spherical powders coming out of our polar dry electrostatic drying systems versus the fractured cake that you would normally see being broke up from the freeze drying process. So if a flowability is an issue or a powder process down the road further downstream is of benefit, this allows us to cut out a few manufacturing steps to be able to get to that nice spherical powder. So again, in conclusion on this study, we have a much faster evaporation rate with our electrostatic drying technology to give us a continuous process or a much faster batch process without really damaging the material as it's going through the process. So that was an aqueous situation. So we also wanted to look at an organic solvent situation. So in this next study, we will take a look at a simulated peptide. So we used 1% BSA as a surrogate for the peptide, but in this study, we will use a 50-50 mixture of water and acetylnitrile. So this would be typically out of the cleansing step of the peptide, but then would normally go to a concentration step where the solvent is then removed prior to lyophilization. So in this study, we wanted to look at the ability to potentially remove the solvent in one step through the drying process without having to take that second step to remove the solvent. So what we see in these studies, we measured this same material feedstock through our R&D scale Model 1, our pilot scale Model 4, and our production scale Model 32. And in all instances, we were able to process this material with 50% ACN without reaching or even coming close to the 410 ppm ICH limits. Taking a look further at the Model 4 and the Model 32 studies, you see our throughputs there of almost 2 kgs an hour on the Model 4 and 20 kgs an hour of feedstock rate on the Model 32, with a total yield of around 92%. Now, this yield we would assume could even be higher as these runs were very short, only 5 hours. And with this process, the longer we run, typically the higher the yield percentage will be. Also, we find BSA to be rather sticky compared to a normal raw peptide. And so we normally see a little bit more hang up using the BSA as a surrogate than we have on actual peptides that we've been able to run. And then you see on the right-hand side where the product temperatures are typically running around 40 to 50 degrees C. So further evidence of why we feel that this technology could be utilized in peptide and oligonucleotide production was the joint announcement we made in January with Sinopep Biotech, where we're working with them to integrate our polar dry electrostatic drying technology into their large-scale peptide manufacturing process. So again, looking at that lyophilization workflow, where typically you would need in a solvent-based application that concentration step, which may still be desired depending on the process itself, we can see that it is possible that we could remove that step from the process using electrostatic drying, as well as any post-processing that would be needed to turn the cake into a powdered material if that's needed for your application. So again, with that, we'll conclude that we believe that the polar dry electrostatic drying can really help cure some of the bottlenecks in production for these very important molecules and other temperature-sensitive molecules, and can really help eliminate some of the manufacturing steps, which, as we know, each step in the process is another chance for impurities, it's another chance for yield loss. So the more we can streamline that process, hopefully the faster, more efficient, more cost-effective we can produce these materials. So with that, one last slide just to kind of show some of the scales of these models, and then I think we hopefully have a few more minutes for some questions. So looking at our current product line, we go from our bench scale feasibility model, which is our 0.1, our R&D scale Model 1, the Model 4, which is typically either pilot scale or even light production scale, and then going into our Model 32 and our Model 50, which are our larger capacity dryers. So when we talk about our model numbers, those are typically the theoretical evaporation capacity of water at maximum conditions, which, again, you have to take that with a grain of salt because, especially with temperature-sensitive materials, you're not ever going to allow the machine to get to maximum operating conditions. But with that, I'd love to thank you all for your attention, and it's great to see such a large crowd here this early in the morning. And if we have some time, I can open up for some questions, and if not, my colleagues and I will definitely be in the hall and can have further discussions later this week. Thank you.
Thank you, Keith. So, very nice overview. We'll start in the back for the questions. Let me get the microphones. Could you please help me? Take one in the back, last row, gentleman standing there. Yep. Go ahead.
My name is Prasad. I'm from Nitto Avicia. Great presentation. Thanks for all the details. I was just wondering, were you able to do any scaled up study for oligonucleotides? And do you have any data that you were able to show today here in this presentation? If not, I can connect with you later on as well.
So I don't have any data that we can show in this presentation here today, as most of the data on actual oligos or peptides have been in conjunction with a lot of our customers. But I can say we did, in Tides US, we did do a joint presentation with Nitto Avicia on some scale-up testing that we had done with some oligos from their side. So we do have some data. It's just a matter of getting the approvals to be able to share that with specific people. But I think you would qualify.
I was expecting some data today, and I didn't see it, and that's why I was just thinking.
We'll move to the next question.
Yeah.
Yep.
That's all right. Thank you.
Yep.
He's taking it right here. Please, next.
Do we have a microphone issue?
Here. There you go.
Thank you so much. Kate, really inspired presentation. You oriented the presentation towards the isolation to replace lyophilization, which is at the very end of the process. I was wondering if there is any limitation or scope of this technology to be applied in the middle of the process. I'm talking about isolation of intermediates, which are in different solvents than just water acetonitrile. Do you see any potential of this technology to be applied on those cases?
Yeah, I think that there'd definitely be an opportunity for it to be used in those cases, definitely with different solvent types. Obviously, we would need to, our solvent duty machines are rated for those applications. We would just need to look at each individual solvent to make sure material compatibilities and everything are fine, but if not, it's just a matter of changing components. So yes, I would believe that we could find some applications for that.
Okay, I'm talking about boiling point and production, for example.
I'm sorry, what's it?
Talking about boiling point, is there any limitation in boiling point of the solvent that you can use with that technology?
Not typically.
Another question in the middle.
Thank you very much. Very interesting technologies. One very simple question for the cleaning. Comparing to the traditional spray drying, are there any differences for the cleaning or cleaning validations for your technology?
Yeah, there would be similar things that need to be considered for validation purposes. I would think it would be very similar, but it is something that we need to work through with each customer as to get it validated into their specific process.
Enjoyed your talk. Can you operate your systems in the presence of salt, and if so, how much can it tolerate?
We have dried salts through the system. as well. I am not the right person standing up here to answer that question, but one of my colleagues that are here with me could probably answer that a little better than I could offline.
Question in the middle. Go ahead, please.
Thank you for the presentation. Susan Q from NITO Avisha as well. I have a question about this system. Can that be integrated into continuous manufacturing? That if your upstream is UFDF, can that continuously feed into this?
Yes, it definitely could, and in some of our applications that is more traditional for us when we look at things like agricultural bacteria or probiotics, where we would typically then vacuum convey that material straight from the dryer off to another process. So as long as that transfer could be done in a sterile way, it definitely would be able to function in a continuous manufacturing process.
Okay, Keith, I'll take the last question
Okay.
with the privilege of the chairman. Very nice work. So if you can comment on two attributes. First, the concentration of the product. If you have a very viscous solution, then your spray drying would be very difficult, I would imagine. So do you have that recommended concentration of the product in solution which you start with for the best results?
So we deal with anything from below, as some of our studies show, down to 1% and even some below. A more traditional application for us would be more in the 20 to 40 and even higher percent solids. I mean, the technology itself was initially developed for an oil encapsulation flavor application. So viscosities up in the few hundred centipoise range is not an issue for the technology. It really now becomes looking at the pumpability and the flowability of the material. But for the most part, if we can pump it to the nozzle and be able to atomize it, then we should be able to dry it.
Sure. The reason I was asking is that some of the conjugates now are fairly hydrophobic that are coming along in the clinic. So that may have some challenge, but maybe you want to look at it later on.
Yep.
And one last question about static nature of the product. So we see that a lot of oligonucleotides after drying are fairly static. Do you see the same thing after spray drying?
So that is going to be very process dependent and very material dependent. But for the most part, what we see is we don't see any real residual static charge left in the particle once it's made its way through into the collection vessel. Because at the bottom of it, everything's well grounded and that is normally discharged off.
So nothing sticks on the surface or anywhere else?
Again, that's really going to be product dependent, but in the oligos that we've run to date, we've not seen that as an issue.
Wonderful. Thank you again. Let's join hands for Keith.